Okay, so last time I introduced Newton's second law. And Newton's second law says F net, the vector F net, is equal to the mass times the acceleration vector. And I want to be really clear about what each of these are. So F net is the sum of all the forces on the chosen object. M is the mass of the chosen object. And A is the acceleration of the chosen object. And I said last time that there are only two, so I want to break up all the forces that are going to be applied to objects in this class into just two types. Two types of forces. The first is weight. That's the force applied by gravity. And then the only other kind of forces that we're going to see are contact forces. And so when problems start to look complicated, you know, a problem looks sort of overwhelming, just remind yourself, I just have to deal with the weight, and then I just have to think about the boundary of the chosen object and look for every place that the outside world makes contact with the chosen body. And if you deal with the weight and you deal with every contact force, then you know you've dealt with the object and you're done. So like, this was probably the example I gave last time, but how many forces are acting on the stapler? There's only two. And that's because there's weight. There's always weight acting on things. And then the only place that the outside world makes contact with the stapler is where the table touches it. And so you know you're done. Okay, so the first thing we have to do is figure out what the force is that gravity applies to objects. So that's the first question. And we're going to use Newton's second law to answer this. So to do this, let's think about an object in free fall, because the nice thing about an object in free fall is we know, well, there's two nice things. One is we know what the acceleration is. It's 9.81 meters per second squared down. And the second thing is when something's in free fall, there's only one force acting on it, and that's gravity. And so we can isolate that gravitational force and calculate what it is. So we're going to think about a 1 kilogram object in free fall. So, well, it could be a projectile, or it could be shot up into the air or out or down or whatever, but the only thing that it needs for it to be in free fall is that there's no other force acting on it except gravity. So, I don't know, let's picture it just being dropped. And let's use a coordinate system with the y-axis up and the x-axis horizontal. The acceleration of the object. So it would be straight down, which is in the negative y direction. So 0, negative 9.81 meters per second squared. And then the mass, we already said, is 1 kilogram. So let's put it into Newton's second law. Newton's second law says the force applied by gravity, that's the only force acting on it, is equal to 1 kilogram times 0, negative 9.81. And if we multiply 1 by this vector, we get 0, negative 9.81. And now kilograms times meters per second squared give us newtons. Okay, so in order to visualize this vector, here's the coordinate system. Plot that point 0, negative 9.81. And that's the point. So the vector is just straight down. With a magnitude of 9.81 newtons. Okay, so this 1 kilogram object, the force applied to it by gravity is 9.81 newtons. And there's like a certain nice, like, that looks sort of familiar. We know that's the acceleration of anything in free fall. So you're sort of tempted to think maybe we're done. But let's try something with a different mass and see what the force is. Okay. So let's say a 100 kilogram object in free fall. So Newton's second law for this one says the force of gravity is equal to the mass of 100 times this object's acceleration in free fall is going to be the same as the other object, 0, negative 9.81. And so this one tells us that the force applied to this 100 kilogram mass is 0, negative 981. And so that's a downward vector with a magnitude of 981. But what we know from that is even though these objects of different masses, any two objects accelerate exactly the same in free fall, the force applied by gravity is different for objects with different masses. So even though gravity accelerates all objects the same, in free fall, it applies different forces to them. Okay, that's sort of a tricky thing to wrap your head around, the difference between that force and the motion during free fall. I mean, if you think about, I've been calling the force gravity applies to things is called the weight. Obviously, different things have different weights. Like you put them on the scale, it says things have different weights. But how do you sort of square this? Like at first it seems like a contradiction. Like how can two things with different masses accelerate the same due to gravity, but have different gravitational forces applied? And the reason it works that way is, remember I said that what mass is an object's ability to resist being accelerated. And I drew the pictures of the truck and the car, and I said if they collide, the truck's going to resist acceleration much more effectively than the car. The car is going to accelerate a lot, and the truck isn't going to accelerate very much. So the idea is that when something's in free fall, say you have two objects in free fall, a 1 kilogram thing and a 100 kilogram thing, and you drop them at the same time, they accelerate the same, but it takes a lot more to make a more massive thing accelerate that same amount. You can't pull on it with the same force and expect it to accelerate the same. It's more resistant to acceleration. And so the force that gravity applies to bigger things is enough bigger that it exactly balances the more massive object's resistance to acceleration and makes the big thing and the small thing accelerate the same. Okay? So they do accelerate the same, but they have different forces applied. Okay, so let's do it now with just a general mass, and we'll figure out the formula. So it depends on the mass. On the object's mass. What's the force applied to an object with mass m in kilograms? Well, Newton's second law says the gravitational force acting on it, so we're thinking about this in free fall again, is equal to the mass of the object times its acceleration. And if it's in free fall, the acceleration is that. And so the force vector is 0, negative 9.81 m. Or you can think of that as 0, negative mg. Where g is the constant positive 9.81 meters per second squared. So gravity applies a downward force of mg to an object with mass m. Okay, so this is the force that gravity applies to an object. We only did this calculation in free fall, but it doesn't matter what you're doing, gravity always applies the same force. So even though we did this calculation in free fall, this is true for an object that's sitting there on something or accelerating in a car and an airplane. This is the force that gravity applies to it. So that's pretty good. Now we know the force that gravity applies to anything we want. Yeah. It doesn't. So this was in free fall. But so what we did was we did this calculation in free fall to figure out the force that gravity applies in free fall. And now we're going to make the assumption, you just have to trust me on this one, that that force that we calculated in free fall is the force that gravity always applies no matter what it's doing. Okay, so that's the idea. Okay, so now let's, we're going to use what we learned about the weight to calculate another force. So here's the example. Okay, so let's say there's a scale sitting on the floor and a person on the scale. And we'll use a coordinate system with the y-axis up, the x-axis over. And we're going to calculate the force applied to the person's feet by the scale. Okay, so Newton's second law says, well, first we have to figure out all the forces that are acting on this person. How many forces are acting? Two. There's the weight force, and now there's a force applied to the feet by the scale. So I'm going to write this as, we know the weight force is, we need a mass for this person. Let's say 100 kilograms. $220 pounds or so. So the weight, what would be the weight? It's 0 for x. For y, it would be negative mass times 9.81, so 981 newtons. So that's the weight. And now we're going to calculate the force on the feet by the scale. And I'm going to assume that we don't know anything about the direction of that force, so we'll just calculate both components. So I'll call it F, X and Y components. That's the force from the scale. And that's equal to the person's mass, 100 kilograms. Now this one isn't in free fall. So what's the acceleration here? 0. The position stays constant, so the velocity is 0. The velocity stays 0, so the acceleration is 0. So the acceleration vector is just 0, 0. And now I'm going to break this up into two different equations. The X component equation and the Y component equation. So for the X component equation, I'm just going to take all the X components, so 0 plus Fx is equal to 100 times 0. So 0 plus Fx is equal to 0. And so what's Fx? And the Y equation says negative 981 plus Fy is equal to 0. So what's the force Fy? Yeah, positive 981 newtons. So this says that that force vector is equal to 0, positive 981. If this is our coordinate system, plot the point 0, 981 and draw a vector from the origin to that point. And so that's the force vector applied by the scale. So 981 newtons up. And so what we learned is if a person is still on a scale and not touching anything else, the force the scale applies to the feet is the same magnitude as the person's weight. And so, you know, that's how a scale works, is based on that idea. The scale isn't actually measuring how hard gravity is pulling down on you. It's indirectly measuring it if these conditions are met. If there's no acceleration and if you're not touching anything else. But you know The Simpsons, where Homer tries to get disability and tries to get over 300 pounds and he weighs himself and his belly's hanging on the towel rack, and so he's like, it measures him wrong. You know, if you touch something else, there's a third force in there, then that equation doesn't work. And just because, so like if you stand on a scale and hang from a bar as you do it, you haven't really changed your weight to 2 pounds or whatever. You've just messed up this relationship between the weight and the force the scale applies to. I touch on something else. Question?
Yeah, so whenever there's just two forces combined, it will always like
Yeah, as long as there's no acceleration. Most of the time there's going to be acceleration in our problems, though. Yeah, if there's two forces and there's no acceleration, those two forces have to have the same magnitude and be opposite directions. Okay, so let's say that this guy decides 100 kilograms, like he's not happy. He's not happy weighing 220 pounds. So he takes the scale onto this elevator. You know, he's also not happy, like, exercising and stuff. So he comes up with this second backup plan. I know how he feels. Okay, so he's on this elevator, stands on the scale, and waits until the elevator starts to accelerate down before he looks at the scale. So when an elevator starts to move, it accelerates for a small amount of time, and then most of the time it's moving with a constant velocity. But just briefly, the acceleration will be somewhere in the ballpark of 1 to 3 meters per second squared. That's, when you start to descend, when you start to accelerate, that's that stomach feeling you get in the elevator, like, oh, that's the acceleration happening. And then once you get to a constant velocity, that feeling goes away. So we want to know, what's the force the scale applies to the feet if the elevator accelerates down at 3 meters per second squared. So I'll still put the y-axis up. If the elevator is accelerating down at 3 meters per second squared, there's the coordinate system. So what would be the acceleration vector? It's in the negative y direction with a magnitude of 3 meters per second squared. So it's going to be 0x negative 3 for y meters per second squared. What forces are acting on the person? Yeah, it's still just the same. It's still the only forces acting on the person are the weight, the force of gravity, and the force the scale applies to his feet. So the force of gravity, so Newton's second law says the force applied by gravity is 0, negative 981, because he still has a mass of 100 kilograms. And then he still has the force applied by the scale. I'll call that Fx and Fy again. And those add up to be equal to his mass, 100 kilograms, times the acceleration. And his acceleration this time is 0, negative 3. So the x equation says the same thing it did before. 0 plus fx is equal to 100 times 0, which is 0. And so fx is equal to 0. And the y equation says negative 981 plus fy is equal to negative 300. And if you solve that, you get fy is equal to positive 681, which says that the force vector applied by the scale is equal to 0x 681 newtons y. And so that's an upward vector of 681 newtons, which is equal to something like 155 pounds. Up here, this was equal to, let's see, where did I do it? About 220 pounds. Oh, let me do it here. Okay, so by getting on a elevator that's accelerating down, you can lose 70 pounds or whatever. But it only works while you're accelerating down, which is only like a fraction of a second or something like that. But that'll really happen, you know. So try it; it's great. And so now let's see what happens if the elevator's accelerating up. I just like drawing this guy. He always looks different and he always looks funny. Okay, so now the elevator accelerates up. Let's say this is at 2 meters per second squared. What's the force vector applied to the feet by the scale? So I don't, it's follow the same procedure, but see if you can work through this problem. Work together, show each other your work as you go, ask me questions if you get stuck, and after I give you a little time to work on it, I'll go through it. Anybody have any questions about that one? Okay. Well, we are going to be doing problems with, a lot of these problems, there's going to be a lot of forces acting on things, and when you're only dealing with one or two forces, it's not much of a bookkeeping issue to keep track of what's what. But we're going to get to problems where it can be hard to keep it all in mind. And so a really useful tool that we're going to use is called a Freebody diagram. So that's the next thing I want to talk about. And I'm going to abbreviate these FBDs because you know how much I love abbreviations. You do, right? Okay, good. Free body diagrams, what the name comes from is, so a free body diagram is you make it very clear what the chosen object is that you're studying, and then you remove all the surroundings. Everything that's not part of that chosen object is removed, so the thing you're studying becomes free from the surroundings, and you replace all of those, the other objects that's making contact with the chosen object by the forces that they apply. So that's why it's called a free body diagram. And here are the, well, this is important, first of all. I'm going to require you to draw a free body diagram every time you use Newton's second law. So in all of my examples, I'll do free body diagrams, and I want you in your work to draw them too. If you don't do it on a test, I'll take points off for that, because it's a really useful thing. So draw a free body diagram every time you use Newton's second law. So here are the steps for drawing a free body diagram. The first step is to draw a closed outline of the chosen object. And this closed outline should have no internal details. And no outside objects should be in the picture. Okay, so if you're doing a free body diagram of the guy on the scale, okay, so that's a closed outline. It's an outline all the way around what we're choosing to isolate. A couple examples that don't work for a free body diagram are like that. That one doesn't work because it's not a closed outline. There's no distinction between what's on the inside of the boundary and what's on the outside of the boundary. And the whole point of doing a free body diagram is to be very clear to yourself about what's included and what's excluded. Okay. Another don't do that. What's wrong with that one? It includes the scale, and we didn't isolate the scale. And then, what about this one, besides the fact that it's a different guy? He's happy. He's doing physics and he's happy. No internal details. Okay. And the reason for these rules is there's only one reason that we put the object in the free body diagram at all, and that's just to be entirely clear about what's inside the boundary, what's inside the collection that you're isolating and what's outside. So with something like this, you don't know whether the scale's included or excluded. With something like this, you don't know, it's, I guess I'd just say that that's extra. There's no reason. It's just muddy, like sort of complicating what should be a very simple distinction between the outside and the inside, the stuff that's included and the stuff that's not. Then the second step is to draw a downward arrow from the middle of the chosen object and label it with the weight, if you know what the weight is, or you can label it mg. But so, for example, if this is object, that's the force vector applied by gravity. Or you could also do it like that. Why did I label this with positive 981 and positive mg? That's sort of I think that's a confusing thing for people a lot of times. All this is supposed to do is give the magnitude. The direction is given by the direction of the arrow. So if you wanted to calculate the components of this, you'd say it has a magnitude of 981. It's in the negative y direction. And so the components of this force vector are 0, negative 981. But the magnitude of the vector should just be that. So it's really an issue, I guess, with confusing the magnitude, mixing up the magnitude with the direction of that vector. And it can give you the wrong signs if you put the negative in here, because if you write this as negative 981, and then, for example, you think, okay, well, if the x-axis is this way, it's 270 degrees from the x-axis to here, and that's correct. But now, say there's a negative here, so you take negative 981 times cosine and sine of 270. That would give you both of the signs backwards. What you want to do is take positive 981, the magnitude of the vector, and multiply it by cosine and sine of 270. Any questions about that? And then the last step is at each place where the outside world makes contact with the boundary, let's see. Draw an arrow in the direction of the force that it applies to the chosen object. I'll just say applied force. And label it with a variable. If you don't know the magnitude of the force, which is most of the time what it's going to be, So label it with a variable, or if you happen to know the value of the force, you can just put the value in. So, for example, the guy on the scale would have a force of 981 acting down from the weight, and then an upward force, I'll call it F, applied by the scale. Any questions about that? Yeah. You can just leave the units off. Okay, so now the next thing we have to do, that's it for the free body diagram, but the next thing we have to figure out is, it says draw an arrow in the direction of the force that's applied, but so far we don't have any way to know what the directions of any of these forces are except gravity. So the next thing we'll do is talk about the directions of contact forces. And there are three types of contact forces that we're going to talk about. The first one is contact along a flat surface. You can think of that as when two things are pushing on each other. The second one is the force applied by a cable, or a string or a rope, or it even, let's just leave it at that for now. So force applied by a cable. And I'll call that one pulling. And then the last one is friction. And that's when objects are sliding. And so one by one, the next thing we're going to do is just go through these. I'm going to start with things that are pushing on each other in contact along a flat surface. Then we'll talk about cables. Then we'll talk about friction. And at that point, we'll be able to deal with any of the force types that we're going to see in this class. Any questions about that? Okay, well, let's stop there, and we'll start with pushing contact next time.